Hello, my name is Michael Riddick. I'm a junior mechanical engineering major from Philadelphia, Pennsylvania, and I'm doing my presentation on the review of regenerative absorption heat pumps. Okay, so quick talk outline. I'm going to talk about the problem motivation, some background information about the design, and about previous articles, some methods and experiments mentioned in the article, results and article conclusions, as well as some self-critique. Okay, so problem motivation basically comes from NASA's exploration vision, where they want to put a permanent lunar base in space, right? But the problem is where they want to put this lunar base has very extreme temperatures ranging from -100 to 100 degrees Celsius. So they have to come up with some type of heat pump in order to elevate the temperature of the environment, as well as interior waste heat in order to send it off into space, right? So some earlier investigations were done by M.A. Lambert, where he identifies absorption heat pumps and mechanical vapor compression devices as the best suited technologies. But the main difference is his principal goal was to minimize the overall mass of the heat pump, which in turn minimizes the overall cost, while this article goes more into depth about the regenerative absorption heat pumps, specifically outlining two principal figures, the overall to improve the overall efficiency, being the coefficient of performance and the specific cooling factor, specific cooling power, which were both mentioned during class. I think during chapter 5 it was. So I'm going to explain a little bit about the basics of the absorbent heat pumps. So when I explain the experiments, you have kind of a background knowledge. And they're heat pumps driven by heat or thermal energy instead of mechanical work. And it's based on the ability of the absorbent to absorb vapor at low temperature and desorb when heated, right? And this is the whole basis behind the whole regeneration component of the absorption heat cycles. And basically, by regeneration, I mean its ability to alternatively accept and deliver heat in alternating flow. So as you can see in the figure, you have the absorbent, which is heated, then it's evaporated and condensed into the other container, which produces a heat output. And in order to set everything back to normal, right, the container has to be cooled, which causes the absorbent to reabsorb and the liquid refrigerant to evaporate, producing a cooling effect. And the regenerative cycle is basically the alternating between cooling and heating. It's basically a cycle. And some methods I'm going to go into are why absorption heat pumps, like why the regenerative variants before compared to the regular ones, the review of literature of regenerative absorption heat pumps, including the different methods of loading heat into the absorbent bed and the different configurations in order to minimize heat loss, and into some critiques. So the first one was why absorption heat pumps, right? I'll go into absorption heat pumps not utilizing heat recycling versus those utilizing heat recycling. And as you can see, during the article, those that did not utilize heat recycling have a lower coefficient of performance. And this is due to heat being lost instead of being recycled back into the process. Its heat is being lost into the environment, which in turn causes you to have to input more work rather than those who utilize heat recycling. And this leads to the introduction of a heat transfer fluid, because those utilizing heat recycling have a higher coefficient of performance. And the heat transfer fluid is basically used to transfer heat in between beds, so more heat is recycled instead of being lost. And the next experiment is testing different methods of loading heat into the absorption bed, because the effectiveness of heat recycling basically depends on how the heat is transferred in between beds and the efficiency of this process. And we go into uniform heat recovery, which is when recycled heat is supplied uniformly to absorbent beds. And the reason why they have a lower coefficient of performance, ranging from 0.5 to 0.65 in a limited heat recovery, is because it supplies a higher temperature heat from the hot bed when trying to cool to heat the cold bed, but only a medium temperature heat is required. And this large temperature difference creates a large amount of entropy, which we don't want, compared to thermal wave regeneration, which has a more efficient coefficient of performance at a maximum 1.1 and a higher regeneration of heat, 70%, because it doesn't have a large temperature difference due to it employing thermal waves that just kind of transverse and move across the absorbent beds to heat and cool them. So it's the difference in the coefficient. The difference in the coefficient of performance is the difference in the temperature difference. So the next experiment is the concentric tube configuration, which was a study to improve the absorbent performance by changing the configuration of the tubes where the heat transfer flows. And basically what this tries to do is highlight the little contact area in this specific configuration, because when you have limited contact area between the inner tubes, outer tubes, the heat transfer fluid, and the absorbent, it limits the number of transfer units that heat could be lost to, like convection and conduction between the walls. And he considered a configuration where heat transfer flow between the inner tubes and the absorbent is contained between the inner and outer tubes in order to reduce contract. And as you can see, he does it for different absorbents, which is done multiple times throughout the article to see how different absorbents react in specific cases, so we know which one to use at the end. And he actually learns how compacting the absorbent to a certain degree will increase the thermal conductivity without sacrificing too much to vapor permeability, right? So as you can see in the diagram, you have the heat transfer fluid flowing in between the inner tubes and the absorbent between the inner and outer tubes in order to limit the contact area. It's a little complicated, but if you take enough time and really look at it, it's not too complicated. So the article came to multiple conclusions, right? And the most important ones to me were how to increase the coefficient of performance, and specifically the ratio of live mass to dead mass, or the absorbent to non-absorbent material, and the overall heat transfer rate. You can see how some designs suffer from a low live to dead mass ratio, and a lot actually suffer from the number of transfer units being inadequate. So because the number of transfer units are inadequate, they're losing more heat without recycling it. So the coefficient performance is lower. The most important one, article conclusion, at least that I saw, was how, like you see mentioned, some designs did not focus enough on the specific cooling power. And also came to some conclusions as to which refrigerant, vessel material, and absorbent to use, including sulfur dioxide for the refrigerant because of its higher specific cooling power, and low medium carbon steel for the vessel material because of its high yield strength and moderate thermal conductivity. Some critiques and questions that I have, right? Some positives was I love this use of graphs and visuals in order to see what the literature, what's being explained in the literature, in order to visualize, because some people are visual learners instead of learning by reading something in its depth of research. And what I mean by that is it's many different articles or different experiments about one specific thing. So you can see different views on the specific research. Some negatives though, I would like it to expand more on why it specifically chose the coefficient of performance and specific cooling power, instead of just throwing it at you like, this is what we're gonna focus on. I would like to know why, and a bit of the organization of data, because some of it overlapped as to one person's research and the other. So it's hard to identify whose research belonged to whom, right? So this is my works cited, and this is the end of my presentation. If you have any questions, please let me know. Thank you.